18 to 22% for unit 3. So this is the biggie here. If we took it and we broke it up into 1/3 chunks, where 1/3 of it we taught it with unit 1, 1/3 of it we taught it with unit 2, and 1/3 of it we put it in unit 4, and that was the gas law stuff that got jammed into unit 4. Okay? But as you can see, there's lots of topics here, so do expect a lot from here. Okay? All right, so first one, and this is the big one too, is looking at the structures and the data so that you can talk about the relative strengths of the forces and things like that. So, you must show work for calculations, pay attention to sig figs and stuff like that. Every time you do sig figs, though, they're not going to mark you off, but make sure you at least make a reasonable attempt to round it. And when in doubt, go with 3. 3 is the good number to go with. All right, so answer the following questions related to the substance shown in the table. Do you predict the vapor pressure of methyl acetate at 293 K is less than 45 torr or greater than 45 torr? Justify your answer in terms of the data in the above table. So we have ethanol, we have methyl acetate, okay? They gave you the Lewis dot diagrams for both. They gave you the boiling points for both, okay? So, vapor pressure versus boiling point. And looking at our structures here, can you identify the different types of forces in our structures? How about for ethanol? What would be the strongest IMF that ethanol possesses or has the ability to do? We see this OH, that means what? Hydrogen bonding is its predominant, okay? Now do remember it also has London dispersion and dipole-dipole. It's just the hydrogen bonding are the strongest out of them. Here with the methyl acetate, this ester group right here, okay, C double bonded to O, O between C's, that means its predominant force is going to be what? Dipole-dipole. It's still polar, and it still has London dispersion forces, but its strongest force is dipole-dipole out of the IMFs. Now, boiling point, this one's higher, this one's lower, 351 for ethanol versus 330. What do you know about boiling point in terms of strength of forces? The higher the boiling point, forces are stronger, okay? At a lower the boiling point, weaker. So, what does that mean in terms of vapor pressure? If you have stronger forces, is your vapor pressure higher or lower? Vapor pressure is inverse, remember, yes. Higher, stronger forces means a lower vapor pressure. So if this is 45 for the ethanol, which we can predict has the higher or stronger IMF with the hydrogen bonding, what should we say about the vapor pressure for the methyl acetate? Should be higher. Should be higher than 45 because its forces are weaker. Okay? So, justify in terms of the data above. Okay? Here is showing you the vapor pressure curve. As you can see, the ethanol versus water, it's standard there. Okay? This is for water versus the vapor pressure of ethanol, as you can see. Vapor pressure of water is a lot lower. Lower vapor pressure, higher boiling point. So, looking at that, vapor pressure of methyl acetate would be greater than 45 because the boiling point is lower than that. Substance that has a lower boiling point will have a higher vapor pressure, and you could probably throw in there with that and say the one with the higher boiling point has stronger forces, or the one with the lower boiling point has weaker forces, and weaker forces means higher vapor pressure. Okay? Identify all the types. We kind of already did that. This one is LDS, dipole-dipole, and hydrogen bonding. The methyl acetate, LDS, dipole-dipole. No hydrogen bonding. And then we're explaining the difference in the boiling points. We kind of already did that. With the additional IMF of hydrogen bonding, that strengthens the IMFs of the ethanol, whereas the methyl acetate only has polar with dipole-dipole forces, therefore weaker. So the boiling point should be higher for the ethanol. So explain the difference. Intermolecular forces present of ethanol are stronger than the intermolecular forces between the methyl acetate. More energy is required to break up the forces in the ethanol, which explains why it has a higher boiling point. Draw a single dashed line in the diagram to represent the strongest type of intermolecular force between these two ethanol molecules. So, question?
Did you say, like, is there say
I would just write it all out.
Okay.
Yes. I think you can do LDS, but dipole-dipole I would write out. It is a known abbreviation for London dispersion forces to be LDS. Dip is kind of my own thing, but you know. Okay. All right. Draw a single dashed line in the diagram to represent the strongest type of force. Now, for seeing ethanol up here, we already decided the strongest force is what? Hydrogen bonding. So hydrogen bonding is going to occur between what two elements in this particular diagram? Hydrogen and oxygen. So it doesn't matter which way you go. You can do this hydrogen to that oxygen, but it has to be off of one of these, like so, because those are going to be the parts of the ethanol that can do hydrogen bonding. Or you could go like this. You could do one this way, between this O and that H. Either one, I think, if you drew it on either one that way. But you couldn't draw like this O. This green one would be wrong. You couldn't do like that. Because that H isn't a polar H because it's attached to the carbon. It would have to be one of the more polar H's, which is off of the hydroxyl group over here, the O to H. So the green would be incorrect. Okay, so stick to the area where the OH is, but one of the O's from over here to the H of the other one where you're on the hydroxyl group, like so. Okay, so the red one or the blue one would count. Okay, so substances that have the hydrogen bonding have to be HF, HO, or HN, as seen here. Okay, hydrogen bond donor, hydrogen bond acceptor. So you could do that one, like I said, or you could do that one. Either one would be acceptable. All right, the structural formula for propanol is shown above. Identify a specific type of intermolecular force most responsible for explaining why one propanol has a higher boiling point than ethanol. Answer by drawing a circle around one of the choices. What did we know about ethanol? How many carbons are in the ethanol chain? There was only two. This one has 3. They both have an OH group off of them. That means their predominant force is hydrogen bonding. So they have London dispersion, dipole-dipole, and hydrogen bonding. Both have all 3. So, which one is going to control the boiling point, though, out of them? They both have hydrogen bonding. So, but we know that ethanol only has 2 carbons in its chain, where propanol has 3. So it has to be dependent on the size of the electron cloud. Which force is controlled by the size of the electron cloud? LDFs. So this one's going to be controlled by LDFs. And remember, you have to say this when the LDFs, because they have all 3, both of them have all 3. So what is making one have a higher property, the boiling point property? It has stronger forces, but it's because its LDFs are stronger. The reason why its LDFs are stronger is it has a larger electron cloud that is more polarizable. That is the key word to say. And more polarizable is going to make it stronger. You have 5 minutes. Okay, just letting you guys know, 5 minutes. Okay. All right. So each is polar. Each has hydrogen bonding. Okay. Oh, here we go. Larger electron cloud associated with greater polarizability. So stronger London dispersion forces. Okay. What you really need to say there. One propanol has a larger electron cloud than the ethanol, therefore the propanol is more polarizable and experiences stronger London dispersion forces than ethanol does. That is a very good way of stating it. Very concise way of getting to the point. All right, looking at this one, we see here, answer the following questions related to the substances shown in the table. Identify the type of interparticle attractive forces formed between one of the substances in the table and a sample of water molecules. Okay, so for example, here we have magnesium. Okay, and we have our H2Os, right? And I think we drew them in class more like Mickey Mouse looking things. What side is a partial negative for the water? Oxygen side is a partial negative. Hydrogen side is the partial positive side. Okay? So this is sort of like when the ions dissolve in water, what forms here? So the water molecules, the oxygen sides would point inward towards the magnesium or the calcium for that matter. Yes, my Mickey Mouses are not that great. But that force that forms between the water and the ion is called what? Ion dipole forces. Very good. So the type of interparticle attractive force here is ion dipole. Okay? Which substance, Mg2+ or Ca2+, will experience stronger attractions to the nearby water molecules in aqueous solution? Justify your answers again in terms of Coulomb's law. Which one should be stronger, Mg or Ca2+? Mg because it's one less principal energy, so its ionic radius is going to be smaller. Very good. Has one less energy level, making its ionic radius smaller, and we know with Coulomb's law, you remember Coulomb's law, we just kind of went over that, is Q1, Q2 over R squared, I believe. Sorry, that 2 should be below. So we're talking about, because magnesium's distance, ionic radius is smaller there, then the distance between the attractive force of the water to it, it will make it stronger. Very good. Ion dipole. Okay, here, according to Coulomb's law, the smaller distance between the charged particle results in stronger attractive force. That magnesium experiences strong attractions to nearby water molecules because it has a smaller ionic radius. Okay. Some more lovely things up here. We have melting point, electrical conductivity in solid, electrical conductivity in liquid phases. So looking at some properties. Each substance listed in the table is classified as a different type of solid, metallic, ionic, network, covalent, or covalent network, or molecular. Based on this information, identify the type of solid for each. So go ahead and take a moment, see if you can do that. Okay, so just like I just said a moment ago, some of you that should be able to pick out the covalent network, or we call it network covalent, doesn't matter, easily because it has this super high what? Melting point, because that's the data point they gave us, but network covalent or covalent network are all non-metals, so should they conduct electricity? No, they shouldn't really conduct electricity. So, okay, so yes, we would label number 1 is going to be the network covalent. Okay. Oh, he's doing number 2 first. Okay. Now, which one? The other one that we should be able to tell automatically is the molecular. Because that's the other end of things. Number 4. Why? It doesn't conduct either in any kind of form, but it also has a very low melting point. So 4 should be our molecular. Now the 2 in the middle, they're a little bit different because sometimes metallic and ionic melting points can be very similar depending on what you're talking about. So really, between those two, you should be looking at the conduction in which phase? Solid phase. Okay? You need to be looking at the solid phase because which one conducts in the solid phase? Metallic. Which one does not conduct in the solid phase? Ionic, because it doesn't have free movable ions. Okay? So that's where you should be distinguishing. So 2 is going to be what? Metallic, and 3 should be ionic. Very good. Okay. We got those right so far. Covalent network and molecular. Okay, as you can see. Very good, very good. All right, as you can see, we have now come into gas laws, which is 3.4, 3.5, and 3.6. Unit 3 stuff. So, balloon contains pure sample of helium gas, a volume of 10 liters, and a temperature of 25 degrees. Pressure of 755 torr. Calculate the mass. Okay? So, you could easily stick with what? What formula do we want here? PV equals nRT. Very good. Okay. Alright, so we plug and chug. We do 755 torr times 10 liters. We're looking for moles because that's the only thing we can get out of here. Now, what is the R value for torr? It's on your formula sheet. Anybody remember which one that one is? It is the 63 what? 63 or 62? I can't remember. Now I'm losing my mind. Alright, hold on. We're going to look that up. Okay, 62.36. Very good. And this is liters times torr over moles times Kelvin. And then we have to do the 25 plus the 273. So this should be 298K. Now once we solve for moles, then we can just change those moles to grams. And we can get the mass. So, let's go ahead and calculate that. Alright, solving for moles. And 3, and 3. I'm going to go with 3. So, 0.40. And I guess technically you could just keep your calculator number if you wanted to. But this is for helium. Then all you do is change it over to change it to grams. Helium should be 4 grams per 1 mole. Like so. So times that by 4. And you get 1.63 grams of helium. Mass of helium. Alright, so here it is on the formula sheet. Now, I don't know why he's keeping that many digits. That seems way too much. So I would definitely round it to 3. There we go. Oh, he did. He rounded it to 3. Good. Alright, balloon rises to a higher altitude. New conditions are negative 50 degrees Celsius. Pressure went down a lot to 0.475. Calculate the new volume of the balloon in units of liter. Assume that no helium escapes from the balloon. So temperature went down and the pressure went up which gas law do we need to do this one? Anyone? Anyone? How many factors are changing here? Temperature, pressure, and we're measuring the volume of change from that. So that's 3 variables. Best is to use the combined. Now, it says that no helium escapes from the balloon. If no helium escapes from the balloon, which one do we cross out? And moles go divide. So all we need is P1 V1 over T1 equals P2 V2 over T2. But don't pass go, don't collect $200 till you change your temperatures to Kelvin. So some people might throw this in there just like it is and not change it, and that would be wrong. So we need 273 plus the negative 50. So this is basically going to be 223K. Alright, and then you just plug and chug basically. So we have, oh, this is ATM though. He did give you ATM. So what do you have to do with your pressures? Convert one to the other. Does it matter which one you guys want? Do you want ATM or torque? ATM. So we're going to take our 755 torque. What do we divide it by? 760. Very good. That equals 1 ATM. Okay, so let's go ahead and do that. Convert that. So 755 divided by 760. 0.993 ATM. Okay, so now we're going to plug in and do that. So pressure 1, 0.993 times the volume, okay, over the first temperature, which is 298, equals, going to erase this to this one, so we know the second temperature. This is going to be 0.475. We want the new volume, and this is over the 223K. And then you just plug in and get your answer and solve for V2. So the volume here, V2, should have gone up to 15.6 liters, like so. Therefore, the drop in pressure, had a bigger effect than the drop in temperature? No, the drop in pressure had a bigger effect than the drop in temperature on this one. Okay, well I did it the combined way. He used P equals nRT, but we both got the same answer. I got 15.6, he got 15.7, but okie dokie. Moles from part A, he's moles from part A. We just used the other stuff. Guess you could do it that way. See, there's more ways to do it than just one way. Alright. Oh, he is doing it both ways. Here, you could do it this way too, showing it the same thing. Got the same answer. Here's the combined way. We did the combined way. Getting the same answer. Okay. Couple more problems, then we'll call it a day. Data for 2 different samples of xenon gas are shown above. Which sample 1 or 2 shows observed pressure value that is different from the predicted by an ideal gas law? Justify your answer with a calculation. Observed pressure. Best thing to do, let's calculate them and see which one does it work well with its observed pressure. So PV equals nRT. So the pressure times the volume, I'm going to do number 1 here. Volume is 10 liters and 0.5 moles. And And since the pressure's in ATM, I'm going to stick with the 0.08206 number, liters times ATMs over moles times Kelvin. And the temperature is 500 K. So let's calculate those both. Do the number 2 as well. Set up number 2 for its pressure, which is 1 liter times 10 moles, 0.08206 times the 500. We'll be able to tell which one doesn't really match its observed pressure once we calculate them. So this one, I'm getting 2.05. And well, this one is 410. Okie dokie. So the one, I'm saying number 2 here, which was the blue one, sorry, I should have marked it, is a little bit lower than it's it's a little bit higher than the predicted there. A little bit higher than the predicted by the ideal gas law. Right? Okay. So let's see where he goes with this one. Calculated it, we got that one. Calculated them both, just like we did. Okay, I see that that one's a little bit lower than its observed pressure. Okay, observed pressure in sample 2 is greater than the value predicted by the ideal gas law. Pressure is higher. Okay, so
what they found was higher than what would be predicted using the ideal gas.
correct. So observed pressure is from the lab is higher than the one you would have calculated using the ideal gas law. Use particle level reasoning to explain why the gas sample you choose in part A has observed pressure value that is deviation from the ideal gas behavior. Okay, so the reasoning here for this one is, had to notice, yes, at lower temperatures and higher pressures, higher pressures usually dictates that the volume is so small, and the volume of the container, I would say, that not the particles, the volume of the container is so small, and because this one has 10 moles versus the 0.5 moles, they don't have a lot of space to move around. So the general conclusion is because it's in the smaller volume of only 1 liter with so many particles in there, that yes, there's going to be some interparticle attraction between them, but they're going to be hitting the walls of the container a little bit more frequently. So, but usually what these questions for deviation in gas law, what you want to look at is if you're comparing 2 for deviations, first thing is look for the IMFs. The one with the stronger IMFs is going to deviate more if they're about relatively the same size. If they're not relatively the same size, one is significantly larger, that means the volume's going to play more of a role because those particles are actually going to take up space. And usually if they're significantly larger, that means their LDFs are stronger because they have a larger cloud that's more polarizable. That will also cause those problems. So those are usually the 2 types of questions that they'll ask when you're comparing 2 particular gases, whether or not they're going to deviate. The smaller they are, with the weaker the forces, the less they're going to deviate. The larger they are, with the stronger the IMFs, the more they're going to deviate. All right. Oh, look at this one. I think we've seen one like this before. Calculate the argon in the sealed 1 liter pressure of in the 1 liter there. So use the particle diagrams. The pressure of the neon one is 1.74, so use that information. Principles of kinetic molecular theory and relationships to answer the following questions. Okay. How many particles are in the neon? Let's count. You gotta count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 particles. Obviously this has 4 particles. Okay? They are both in the same size container. Okay? And they are at the same temperature, so we know temperature is the same. So we can basically, to figure out the pressure of the argon, do what? A proportion, right? Okay, so we have 12 particles for the neon over the 1.74 equals the 4 particles for the argon is going to equal whatever that pressure is. Because they're at the same temperature and the same liters, they are proportional there. So 4 times 1.74 divided by 12. .58. I guess I would go with that. 3, because this has 3, but same temperature, same liters. You count the particles that are equivalent, because the particles are pretty much relational to the pressure. Look, P is directly variable when V and T are the same, using pressure over N. I didn't do it that way exactly, but I mean, I didn't declare it that way exactly, but that's what I was doing. Okay, so 12 particles, 4 particles, we did that. Relative number of gas particles shown, argon vessels should be 1/3. 0.58, we got 0.58, good. All right, indicate whether average kinetic energy of the neon particles is less than, equal to, or greater than the average kinetic energy of the argon. Please, nobody miss this. Equal to, thank you, because the average kinetic energy is a measure of the temperature, and if they're at the same temperature, they have the same average kinetic energy of the particles. That is defined as a postulate. Kelvin is a matter of proportional to the average kinetic energy. That is one of the kinetic molecular theory postulates. So they have this same average kinetic energy because they're at the same temperature, and they told us they were at the same temperature, so their average kinetic energy should be the same. Okay? So equal to, same average kinetic energy. Don't get that confused with the particle speed, because that's a different concept, okay? All right, indicate whether the average speed, which is our next question, which I knew that was coming, of neon is less than, equal to, or greater than the average speed of argon. Okay, what equation should we cite here? Who knows it? Kinetic energy equals 1/2 mv squared, because if they're at the same temperature, this is kinetic energy 1 should be equal to the kinetic energy of the second one. So if this is neon, this would be argon. Okay? Now, what you have to take and consider, what does M mean? Mass. And V is the velocity or the speed of the particles. So, we look at our masses of argon and neon. So, which one has a larger mass, neon or argon? Neon? No, argon's bigger, right? Argon's bigger. So, you would need to say, because they're at the same temperature, the average kinetic energies are the same, so it would be based off of the mass, because kinetic energy equals 1/2 mv squared here, okay? And we would say that neon is got a smaller mass, so therefore it should be on average speed going faster, okay? It is greater than the average speed of argon because argon is more massive. But make sure that you talk about or cite the equation in there. Same temperature, the average kinetic energy is the same, so 1/2 mv squared here. We're looking at the mass of the particles. Neon being smaller means its average speed should be greater than that of argon following this equation. So let's see what is written here. Okay, 1/2 mv squared, as we can see. Okay, so neon particles are lighter than argon particles, therefore the average speed of neon particles is greater than the average speed of the argon. Alrighty. Last but not least, calculate the total pressure of the gas mixture. Okay, you're basically taking both of those gases and sticking them in the 2 liter. What is the one thing that mainly everybody forgets to do with this one? Add the volume.
Multiply.
Divide by the new volume. Divide by the new volume. Thank you. All right. So you can actually do this one of 2 ways. You can do them separately, you know, by doing the P1 V1 equals P2 V2 separately for both, and then add them together. So you could do that way, or you can like count the particles, put them in there to add those pressures, or add the pressures together that we got, and you divide it by 2, because the 1 liter plus the 1 liter equals the 2 liter. So you could do this separately for both and then add them together, or you could do this, add them together because we figured out the other pressure, and then divide it by 2 liters. Either way, we should get the same answer, so go ahead, calculate that. We'll go over his answer, but if you got this, then you're good. 1.16 either way, you get this as the total pressure.
I'm calling Chris and he wants to know if you're still here.
You're like this.
So divided by 2, we got that. We're good to go. How about that? Very good.